Hello, everybody. Welcome. I'd like to introduce Doug Hellman, who will be speaking to us next about building a debugger. So take it away, Doug. Thank you.
All right. Good afternoon, and thank you all for coming. As Peter said, I'm Doug Hellman. I'm currently working as an OpenStack contributor for Red Hat. But today I'm going to talk about a different project. I'm going to talk a little bit about how I glued together some modules from the standard library and some things that I downloaded from the internet to build a Python power debugger. The project that I'm going to be talking about runs alongside your program, and it collects all of the information about which lines of every file that are executed and all of the values of the variables as the program executes and how those change. And it records all of that information for you so you can review it later. Before we go too far into detail, though, I want to make sure that I've set your expectations clearly. Most project-based presentations at conferences like this are set up to cover the features of the project, and they really talk about what the thing is and what it does and maybe how you can use it and include demos and things like that. And those are great talks, and it's a big part of why we all come to conferences like PyCon, to learn about new tools and things that we can add to our toolkit. But that's not what I'm going to talk about today. Instead, I'm going to talk about how I built the tool. It's easy to forget when you see a presentation like that those tools they don't spring into the world fully formed. They are created over a long period of time with a lot of effort. And during the years that I've been leading the Python meetup in Atlanta, I've found that the best received talks that are given at the meetups are the ones that talk about not just how to use a tool, but how a project that uses a tool was created, the mistakes that might have been made along the way, things that they had to go back and do differently. And so that's what I want to do today. I feel like it's important to talk about the evolutionary process for projects and how you build complex things from simple things. So what I want to focus on is the thought processes that I went through during the implementation rather than the details of the tech itself. I'm going to show code. I'm going to talk about the toolkits that I used as I tell my story, but I want you to think about the process that I went through rather than just the little details about how the data is being collected and things like that. All right, so first things first, what's up with the name? When I started thinking about the design for this tool, I was thinking about it as it's kind of spying on what your program is doing because it's collecting all of that information. So of course, I started thinking about spy names. This guy was a little too obvious, so I decided not to go that way. I wanted something a little more subtle. So I chose George Smiley, the John le Carre character. He's a little more intellectual, a little less flashy, and that's kind of my style. Plus, you can't really go wrong with Alec Guinness. So, all right, so with the name out of the way, I could get down to the real business of starting to plan out the feature set for the program. So I knew that I wanted to record all of the data that was changing in a program. I wanted to be able to replicate the features of PDB without having to tediously step through all of the lines of code as you run your program or find all the places that you need to set breakpoints and that sort of thing. But I also wanted to combine that with the best of print-based debugging, where you just dump a bunch of information to a log file or to the console, and then you just sort of look through it all at once afterwards. But I also didn't want to have to decide up front which values to print out and how to format them and things like that. So I knew I wanted to record all of the calls and all the data. I wanted to build in from the beginning the ability to debug remotely so that I could run a program on a server. We all run everything in the cloud these days, right? So run a program on the server, collect the data on my laptop, and look at the results there. And then I knew I was going to need a way to browse that history of different runs and different sets of output and analyze all of that locally. I was also motivated to sort of try and build something a little bit audacious, to see how far I could take the idea. When I started out, I didn't know if I was even going to be able to build a thing that does what Smiley does. And I also wanted to work in some opportunities to learn some new tools. So this was a side project. The point of it was just experiment, play around, but I wanted to learn something along the way. I had worked in the past with Python's trace API, so I knew how to sort of tap into that and get the data that I wanted. I've done network programming before, so I knew that if it came right down to it, I could just do raw socket work and do the remote execution part. But as part of learning, I decided I wanted to try out ZeroMQ as a networking library. That was new to me at the time that I started Smiley. Working with ZeroMQ involved reading a bunch of documentation, writing some experimental scripts, looking at the different models that it has and trying to figure out which socket types I needed to use and things like that. And that took a couple of weeks of experimenting and getting things wrong. And I think it took that long because I made a bad choice early on in that process. Initially, I used the pub/sub socket type because I thought if I was running things remotely and debugging remotely, I would want maybe multiple listeners, one to record and one to show me things on the console, that sort of thing. But it turns out that pub/sub doesn't guarantee message delivery. So after a few very frustrating debugging sessions, I discovered somewhere in the documentation that it said that delivery was not guaranteed. And obviously, for a debugger, you can't lose information because it would not help you debug your program. So I switched from pub/sub to push/pull at that point, and experimenting with that and with the pub/sub socket, I had created a pair of classes that I was able to use in the creation of Smiley to abstract all of that communication aspect away from the application. So the application used the publisher and the receiver classes, and then those would be re-implemented over time, different ways as I was doing my experimentation between pub/sub, push/pull, or even if I eventually decided not to use ZeroMQ, I could just replace those classes. So after I had those implemented, I created a tracer class. That works by tapping into the sys.setTrace function in Python so that every time the Python interpreter does anything with your code, it calls this function that you've registered as a callback, and it passes it the stack frame that's being executed and an event that is a string that sort of tells you what it is that it's doing. So it'll be like it's calling a new function, or it's returning it from a function, or it's just executing a line or something like that. So using this, I was able to collect all of the information about what the program was doing. And then the work for sending it over the events, sending the events over the socket was done by another class, which figures out first whether or not the event is even of any interest. So I started out ignoring all of the things that were happening within the standard library modules. That's a little more flexible in the version that you'll look at if you download the code today, but at the beginning, I just ignored the standard library completely. So if it decides that it should record the information about the event, then it builds a list of the interesting local variables from that stack frame. So the frame includes everything that's visible, so you get modules and classes and methods and functions and things like that. And those don't really change over time, so I ignore those and collect all of the other variables. And then finally, it builds a standard data structure so that all of the messages going over the wire look the same. So it includes the message type and all those local variables and a couple of other little values that are of interest as you are looking at the replay. All right, the next step was to build some sort of UI. So at this point, I have 3 or 4 different little classes that work together, but there's no way to actually run them. They're just standalone classes. So I'd started out with some simple standalone scripts that used argparse to parse command line arguments. But then as I built more and more of these things, I realized, I'm kind of doing a bunch of one-off scripts, and it would be better to build this in a way that was going to be more flexible and more extensible. So I switched from doing individual scripts to using the Cliff command line framework. That's a framework that uses argparse for parsing the command line arguments, but it also uses setup tools entry points to discover plugins for subcommands. So anyone can write a new plugin for Smiley and distribute it in their own package. It doesn't have to be built into Smiley, and then Smiley will just discover it, and it'll be available for use. So that seemed like a good feature for a development tool like this to have. So I started with a run command to set up the trace code and publish events to a ZeroMQ socket, and then I wrote a monitor command to listen for those messages and just print them to the console. Both of those default to using a localhost socket, but because it's ZeroMQ, it's possible to specify a different URL there, and you get remote monitoring, and it's just sort of built in for free. The monitor command sets up a listener that calls a method every time it gets an event over the network, and it includes a simple little if statement, just looking at the type of the event and doing a little bit of formatting differently, so the start run and end run are a little bit different than the individual trace lines. And to test all of that out, I created a little input script with a few functions that are doing not a whole lot of complicated stuff, but some interesting things, including like a generator and some looping and some recursive calls and that sort of thing. So I could run smiley run simple.py in one terminal to run my test script, and then in another terminal I could run smiley monitor, and that would collect the output. And you can see it's not terribly readable, but at this point it was good enough to show me that I was actually communicating and sending all of the data that I had been collecting. The output includes the event types. It also includes the file names and the line numbers of what's being executed. And then once it's inside of a function, it shows the function name that's being executed as well. So at this point, I had the ability to run a command, trace a program, send those results to a remote system, to the monitor command, which would then put everything out to the console. And that's a good early step, but it's not really a minimum viable product for a debugger like this. So the next step was to figure out where else I was going to send that output and what else I was going to do with it. I decided, since I knew I wanted several commands and I might want to write to different kinds of output destinations, I needed to do a little bit of cleanup work to refactor the existing monitor command and make a reusable base class for that. So I chose to start with that and work on recording runs for browsing and replaying later. And I knew to do that, I would want to store them somewhere in a database or a data file of some sort. We have a lot of options for databases in the Python community. Every database has a Python adapter, it seems. I've used in the past ZODB and MongoDB with pretty good results for different purposes. Neither of those quite had the query semantics that I thought I was going to want for Smiley. I knew I was going to be doing some summary queries, like how many trace elements were there and things like that, or maybe some filtering and stuff like that. So after thinking about how the replay command was probably going to want to work, I decided that I was just going to need to use a relational database. And as a developer tool, I didn't want someone to have to install a separate service to write the data to a separate service. So I decided to use SQLite. It's built into the standard library. It's available there when you run Python on most platforms. So that was going to fit the bill. Now, I didn't use an ORM to talk to the database, but I did create an abstraction class that identifies the logical operations that I want to do with the database and separates the representation in the database from the representation in the program. And I started out just with a simple start run that just creates that initial record when a new program has been run and the data collection has started. And what that let me do is test out end-to-end that I was collecting data, sending it over the socket, writing it to the database, and my transactions were working correctly. And then I expanded that API, the database handle, for all of the other events that were going to be collected. So the record command that writes to the database has a method for processing messages, and you see it's got this if statement again where it's looking at the message type. Normally when you see a pattern like that repeat, where you're looking at types or you're doing a branch like this, you want to try and figure out a way to eliminate that. The typical way to do it would be to create a specific event class for each event message type. But in my case, I decided that it was actually better to just stick with the if statements because I wanted all of the database logic to be in one place. I didn't want it to be scattered across all of the message types. And I wanted all of my formatting logic similarly to be in one place. I didn't want it to be all built in to the message classes. So I just stuck with simple dictionaries as messages. So after I had all of the pieces working to record the start of a run, I updated it to handle the other kinds of messages so that I was actually collecting all of the data about the run. But iterating like that one method at a time let me focus on one thing at a time. So I only had to worry about the 0MQ communication or the trace module or getting things formatted on the console or the pieces of the database handling one step at a time. So I didn't try to build the whole thing all at once. All right, now I have a basic way to record the run of a program, and it goes into a database, and I had to decide what aspect of the program to tackle next. So I could start building the database query API so that I could replay old runs and print that information to the console, or I could look at sending some more complex data types. So I had, at this point, a single line string, basically, so that if your program exited with an exception, you would get the error message and it would be recorded, but you didn't get the full trace back. So I thought that was a pretty good example of a specific complicated data type of full traceback that I could work on and get that data sent across the wire and recorded in the database in a useful way. And then I could expand that for other kinds of classes. So I wrote a little bit. It uses JSON encoding for its wire protocol. So I wrote a little bit of custom JSON logic to look at the thing that is being encoded. If it's a traceback, it uses the traceback module to extract the traceback structure. And if it's another kind of an object, it just looks at it builds a dictionary, and it puts the class name and the module name from where the class came, since class names don't necessarily have to be unique. And then it just stores all of the extra attributes from the object in that dictionary. So it's a really simplistic representation of the object, but it's serializable in the JSON. Okay, so now I have a thing that can send all of this complex data across the wire, but I still have no way to look at it afterwards. It's just going into a database. I knew I had the formatting code in the existing monitor command, so I started refactoring that out into a separate class so that I could reuse it for my replay command. And that's when I had kind of an epiphany about what I was doing. It seems like a really small thing in retrospect, and it's probably obvious, but at the time it made a really big difference for me to realize that the output formatter, the database handle, and the ZeroMQ publisher all were basically doing the same three things. They needed the same three methods. So I created a base class, an abstract base class, to represent what those operations were, and refactored all of the existing code to fit into that abstract base class. That let me go on and work on the replay command using the existing code, but I realized immediately that there was no way to test that because I had no way to get a list of runs from the database. So in order to write a replay command, first I needed a way to get a list. So I wrote a list command, and then the replay command was a pretty straightforward implementation using that event API that I'd created. Basically, I had to add a couple of methods to the database to get the data out, and then I just iterate over the formatter calling the right methods. Around this time, as I was looking at old runs, I discovered an issue with storing that data. The monitor and replay commands show the line of source code that's being executed as each step of the program progresses. So that was implemented originally using the line cache module, which just takes a file name and a line number, and it gives you back that line of that file from the file system. But as I was looking at older and older runs, I realized that replaying those old runs, I was getting the wrong lines. It was not the right values. So I realized that as I had changed my input program, the recorded output data was no longer valid. So I added some calls to the database API to let me store the source code there in a separate table. So as you run your program, it actually sends a copy of the source over the wire and stores it in the database so that it's recorded along with the version of the program, the output that you're collecting. And then I created a DB line cache class that takes a file name and a line number, but instead of reading from the file system, it reads from the database. It's not really complicated, but by designing it the same way that the line cache module works, it meant I could just drop it in, and the existing formatter code didn't have to really change at all. So at this point, I was running the record and run commands over and over again, and those were I had to run those in separate terminal windows, and I was getting a little bit tired of using them as two separate commands. So I wanted to keep the record command as a separate thing for debugging, but I knew if it would be more usable for local debugging if I just told the run command how to write directly to a database. So to do that, I needed to teach it how to write a database instead of a socket. And since the database API was in part derived from the same event processor API base class, I knew I could just instantiate the database and pass it in instead of the output formatter. So I added a command line flag, and I just dropped the database in there instead. So that's two cases where identifying an abstract API let me provide a concrete implementation with really maximal flexibility. So now I had something that was usable for very simple Python programs, and the iterative pattern of what I was doing should be really clear. So I would learn something new, I would build a feature using it, and then I would evolve that feature, either enhancing it or fixing the inevitable bugs, and then I would start on the next feature. And so far, I've talked about 9 different iterations of that, starting with ZeroMQ and SQLite, moving through the various smaller usability enhancements. As I was working on all of these different iterations, I was building up a very big database of test runs for my test program, and I wanted to have a better UI for browsing them than running the list command, finding the right GUI value, and then putting that into the replay command. So I transitioned to the next step and started building a web interface for it. This is definitely a case where I had to go outside of the standard library. So for a CSS framework, I started with the pure CSS library. I realized that I had used that on my blog, and that was pretty good, but decided to switch to Bootstrap about partway through because it has better widget support, and I was building something more interactive. And then I chose Pecan as a web framework, mostly because I'd used it recently, and I know the developers through the Atlanta meetup. So starting again, I created basically an analog for the list command, which is a list of all of the runs in a web view. Then I added links to the left column there to provide a way to get to the view for the trace output itself. That shows each line of the script being run, just like the console program, but it's a little bit easier to read because of the formatting is improved. And then I wanted, for the command line tool, you just use your editor to look at the source code, but for the web app, I wanted to be able to show that old code that was in the database, so I added a view for that. And of course, looking at plain text in a web browser is pretty boring, so I hooked up the Pigments library to it so that we could get syntax highlighting. So that's a nice improvement over the plain text. It was a little more challenging to add syntax highlighting to the trace view itself, because that's showing one line at a time, and that might not be a completely parsable expression. So Pigments might not understand how to parse the statement. So I wanted to feed the whole file into Pigments and then pull one line of it out at a time. So I noticed that the Pigments output just had, it had basically your source code in the same format with all the same white space, and then it had a prefix header and a suffix footer at the end of the blob. So I wrote a new line cache implementation that reads that, strips off the header and the footer, and then gives you back just the formatted lines. And again, I was able to drop that in and replace the existing formatter, or the existing line cache implementation. And so I get syntax highlighting in the statement column now. The local variable definitions were a little bit easier to deal with because those were already full, well-formed expressions, so I could just pass those directly into Pigments. And then at that point, I have basically a complete usable interface for looking at the trace history. I also wanted to build in a feature for collecting profile data so that I would understand, where the program was spending most of its time. I originally thought I was going to have to build a profiler myself because I was using the trace module, but I looked again at the profiler API and the trace APIs, and I realized that because they use different hooks, they could both be used together. So instead of building my own profiler, I just turned on the built-in profiler and collected that data, sent it over the wire, and stored it in the database. So then I had a web view to show that as a table, and then Ryan Petrello showed me how to generate a visualization from that, so I added a view for that. And that shows you the different colors represent where the program spends most of its time at that level in the program. All right, so after I'd added profiler support, I kind of hit another plateau with the feature work, and I was looking for the next thing that I was planning I needed to do. I noticed that the web UI was showing a lot of the same data over and over again, so I decided to change that so that it only showed the local variables when they'd actually changed. And then I also thought about how important comments are when you're looking at a debugged program, so I decided to try and make the line cache program show the comments around the code that's being executed. So the first version of the variable collapsing code used the difflib module on a sequence of variable names and values, and that worked pretty well. The difflib output is basically a list of changes, so you know what's been added or removed or changed, and that told me what I needed to display. So I was able to remove the duplicated data by comparing those variables from one line to the next. Anytime execution enters a new function, it sort of automatically triggers redisplaying everything from that function because the context has changed. But within a given function, only the variables that actually change are displayed. Now that gave me output with lots of lines with no variable output at all because the variables in my particular sample program weren't changing that much, and that gave me the idea to collapse those rows together and show them as a block of source instead of an individual line. And so I wrapped the existing iterator that was pulling data out of the database with a generator that collapsed that into aggregates and gave me a range of lines. And then I updated the line cache modules so that they could pull out a range of lines instead of an individual lines to make it easier for the template code. And then I had a nice place in that getLines method of my line cache code where I could add a little bit of logic to sort of look for comments around the code. So I was able to take in a range of exact lines that had been executed, and I could search backwards in the file and look for comments. And at that point, I was doing a lot of processing in the user interface, and it started to seem slow. I knew that was really only going to get worse as my program runs grew longer. So I decided to add pagination to the interface to address that. And then after pagination was working, I added some other features. So if you have a multi-threaded application, it records which thread each statement is being run in so that you can, in the user interface, filter out and just look at one thread at a time. There's a command for generating static HTML output so that you can put the results on a website and share them. And there are also commands for exporting a run from the database and importing a run so that you can collaborate with someone else. So if you record data, you can share it with your colleagues, and everybody can look at it. Now, when I told this story at my meetup group a year or two ago, I called Smiley a weekend project. And someone in the group misunderstood that to mean that I had written it over the course of a single weekend. Which, right, I wish, right? In fact, it took me 2 years to write Smiley in my spare time. And this chart shows the days on which I had commits, and then the y-axis is the number of lines of code. Lines of code is a terrible metric, but if you accept lines of code as a kind of an analog for complexity and project growth, which for a brand new project, it seemed like a pretty good metric, you can see that over the course of time, it grew pretty steadily. And I've described how it grew from a very rudimentary program to a much more complicated program with a server mode and web interface and all of that sort of thing. The only real exception to that sort of steady small growth is that right around the end of 2013, where over Christmas break, I added that HTML report export feature, and I checked in a whole bunch of CSS libraries and template code and vendored all of that inside of Smiley. And so that was sort of one large commit with checking in a library, but it was not code that I actually wrote myself. Now, if I had been working on it full-time, rather than in my spare time, I still think it probably would have taken me a couple of months to implement the whole thing, because what the graph doesn't really show is all of the time that I spent between commits doing all of that research, experimenting with things, figuring out that I was going down the wrong path and deleting code, throwing things away and starting again. So while I've compressed the story down into 20 or 30 minutes here, it really, really took a lot longer than that. And it's not done. So there are a bunch of things I'd like to do. For one thing, the performance is pretty terrible, as you can imagine. So working on capture performance is probably the biggest need. Pre-calculating and storing a bunch of things that the UI is going to render, that would actually improve your browsing experience as well. And there's a bunch of little things that I'd like to add to it too. But in addition to possibly enticing some of you to contribute to Smiley, the purpose of my talk today is to inspire you to write or talk about your own projects in the same way. So whether you write on your blog, or you talk at a meetup, or you have a paper accepted at a conference, it's important to talk about the process and the decisions that you make, and the mistakes that you make, and the iterative processes that you go through, and talk about how you did things, not just that you did things. So I hope that you will, in the future, share your experiences and not just your results. Thank you for coming.
Thank you, Doug. I think we actually have time maybe for one question.
Okay,
are you open
sure.
to that? Is there one question in the room, either side? Over here, yes, thank you.
Do you feel like you accomplished your goal with Smiley? if you had a goal at the beginning?
Yeah, so that's a great question. I do. I learned a little bit about some of the tools that I was using, so that was sort of my selfish goal for doing it. The program itself is a bit less usable than I had hoped right now because of the performance issues, but I think those are addressable. And it gave me a good story to tell today and at other conferences, so I think that was sort of a good side effect that came out of it.
Thank you.
Cool. Thank you.
Okay, let's thank Doug again.
Thank you all.